Hello everyone, welcome back with this series of Power Hour for your NEET 2025, and in this we are going to start the next topic of magnetism. Alright, so I guess by now you have been preparing for your NEET exams quite well, and most of the topics or the theory points you would have revised by now, and you are practicing a lot of questions. Okay, so keep on doing this only till your NEET exams, and don't take any unnecessary burden, don't take any unnecessary stress. Just keep on solving the questions, keep on practicing your PYQs. That's it, nothing else to worry about. Alright, with that we'll start the next topic of magnetic effects, magnetism. In this, I know that most of the students just focus on the formulas, and that's perfectly fine. If we remember the formulas, then we can certainly solve most of the problems of magnetism. But remember that the basics are always somewhat similar. What are the basics? If you remember from your electrostatics, the Coulomb's law was there, the electric field was there, and the force and the energy, so many things were there. Then the dipole was there, and if we keep the dipole in external electric field, what would it do? It will experience the torque, because the net force on a dipole in uniform field will be 0 to experiences a torque, and it can possess some energy. The similar kind of effects we can see in a magnetic dipole, which is nothing but a bar magnet. And you know that due to a charge configuration, due to a line charge, we had electric field formula 2k lambda by r, and sine alpha plus sine beta. These kind of formulas you always have. So in the same way, there are formulas associated with magnetism. Just like in electrostats you had a ring charge, and at the center we say the field is 0 due to the ring, and then we had infinitely large line charge 2k lambda by r electric field. So similarly we have infinitely large current carrying wire, and due to which we'll find the magnetic field this time. Okay, so let's carry on with the topic of magnetism. We'll start with the magnetic field due to current carrying wire, and in that series I guess most of you guys remember what was the first law which we studied. It was the Biot-Savart law. So let's get ready with that. Acha, first of all, how many problems we can expect? So if you see from 2015, it's about 3 to 5 questions, and later on after that we can see around 3 questions on an average they ask from this topic, magnetism. So it has sufficient weightage if we say like that. Okay, so let's quickly get on with the Biot-Savart law. What is it for? Finding the magnetic field. Biot-Savart law for finding the magnetic field due to a current carrying wire. We are going to write the proper Biot-Savart law, the general format, due to any randomly shaped current carrying wire. Suppose there is a current carrying wire and we are only focused on a very little portion of this wire. It's carrying I current. Let's consider that this portion has a length dl. Okay, and here if you see that I have written dl as a vector quantity just for the sake, because if we write the field then it's a vector quantity, so we'll need some vectors in the formula. That's why like this. I say that current through the wire is moving along the wire. So at a point, if I take this dl element, we always take a very little portion and we call it element. I'll draw a tangent to this element, and the direction of the tangent will be taken as the direction of dl along the current, because current can go upwards or downwards, forwards or backwards like this. So along the direction of the current and tangent to this. Now from this little section, what I say ki there is a random point situated near this wire somewhere. I don't know where it is, it can be anywhere. And the line joining this element and the point P can be considered as another vector, which I can say as the position vector of that point P, when it is starting from this little section of wire, DL section of wire. Okay, so it is another vector quantity and this is another vector quantity. Get it? Just for the sake key, I'll write the magnitude of r vector as r. Tick. Now some quantities I must understand for this. Ki Biot-Savart law says that the magnetic field due to this little current carrying wire or the section of this little current carrying wire is equals to mu naught upon 4 pi I is the current as it is, dl cross r vector. This is a vector, another vector multiplied through cross product because magnetic field is also a vector quantity, divided by the magnitude of this vector is r, so r cube. This is the magnetic field. And now what is this mu naught? This mu naught is called the permeability of vacuum. Okay, if we are writing the Biot-Savart law in vacuum, then its value is 4 pi into 10 to the power minus 7 in SI units. This is your straightforward Biot-Savart law. A little point I would like to make a note of here is कि if you are writing dl cross r vector, then in the denominator you will get r to the power 3 r cube. Sometimes in some books you see that it will be written as I dl cross r cap, and I would like to just remind this ki what is the r cap. R cap is a unit vector which can be written as r vector upon the magnitude. Unit vector just denotes the direction of any vector you want along that unit vector. So if I write IDL cross r, then in the denominator it will be r square. Why? Because r cap is nothing but r by r. So I'll take one r outside and r vector divided by r becomes what? R cap. So it is the another form of your Biot-Savart law. Okay? Like this. Biot-Savart law takes a very general formula and we can extrapolate this thing for different wires and different shape of wires. Let's say for a straight current carrying conductor of finite length, I want to find the magnetic field. Okay, so let's proceed. Next is magnetic field due to a straight current carrying wire. So I'll take up this example. Okay, suppose there is a wire and it's not just this key, it is starting from here, it's ending here. No, it may be a part of a circuit because current will only flow if the circuit is complete. I cannot take just one little wire and out of the blue there is current in it. No, it should be a part of a closed circuit. It should have some components around in the whole circuit. Just that I am considering the magnetic field only due to this section of the wire. Okay, wherever it is present in the circuit, that's none of our concern. I just want this section of wire and I'll find the magnetic field due to it. So I say that there is a point okay, at a distance r from this wire, and if I join the topmost point of the wire with this point, then the line joining A and P subtends some angle alpha with this horizontal line, which is just the perpendicular distance from the wire. Okay, and please make note that this is not the midpoint of this wire at all, as you can see in the diagram as well. Get it? The lower point of the wire and I join the B and P angle, this line BP subtends with the horizontal, but in the downward is beta angle, some different angle, can be anything, it's a general scenario. ठीक है, alpha can be 45, beta can be 30, alpha can be 30, beta can be 20 if we know the values of sine 20 and like this. Okay, now see, this wire will have some length obviously. Okay, I want to find the formula, then I need the length. Definitely I need the length. I need this distance also, because this distance will be required in this formula. Now the issue is ki, to find the magnetic field, if we go in the derivation, I'll take a little element here. What we do, ki due to this little element, if I just zoom out this portion, here we'll zoom out, so it's nothing but it is also a little section of wire whose length is dl length, right or not, and it is carrying some I current, and due to this I'll find the magnetic field at that point P. Get it? The line joining this little element, now see, since the length of this element is very less, so these two lines are kind of having the same angle with the horizontal. This angle and this total angle is theta plus d theta, while the d theta is very small, so they both are kind of having the same angle. Okay, now due to this, if I'll find the magnetic field, just tell me what will be the direction. This is your r vector. If you go back and look at this formula, it is I dl cross r. So r vector is just the vector starting from the element to the point P. Vector starting from the element to the point P. If I make the r vector from here, then it is the r vector in this direction. The formula was I dl cross r. dl is this. It's going upwards because the current is going upwards. Tell me if you remember something about the cross product. So dl cross r, how to find the direction? Where the current is going upwards, so dl is like this and r is like this. So what I need to do, I'll put my hand along this current carrying wire, the length of this wire, and the r distance is like this. So I need to curl my hand towards this r. So I'll start from this here. Okay, this current direction, I'll curl my hand towards this r. So just look at the thumb. If I am curling my hand, curling the fingers in this direction of the right hand, then the thumb is pointing inwards into the plane. That means if the wire is in this vertical direction and the point or the distance r vector is somewhere in the xy plane, then the magnetic field has to be perpendicular to this wire as well as this r vector, the distance of the wire and that point P. It has to be perpendicular to both. So what is the direction perpendicular to both? It is the z direction. I can say either it is going inwards or it is coming out of the plane, the z direction. Get it? As per this wire, so current is going upwards, that particular sense of current gives me the direction of magnetic field which is into the plane for this scenario. But for any other scenario, it can be anything else. Okay. So I got the direction of this vector along negative z axis. Get it? Okay. Now I am writing that thing, and suppose ki this angle is theta, so I can say that I need the angle between the current carrying wire and the r vector. So if this is angle theta, then what will be this angle? Tell me. It's going to be 90 minus theta, and this is just the zoomed effect of this little element here. So I'll write the cross product. I know that the little magnetic field is mu naught upon 4 pi Okay, I dl cross r and r cube. Okay. Let's just expand this cross product. So dl cross r will be dl into r into sine of angle between them, which is 90 minus theta. So this is my little magnetic field, and we are just about to get the final result after the integration. The direction will be into the plane, so I get that all the little elements are going to have the magnetic field into the plane. So integration is very easy. All the net magnetic field is going to come out into the plane. So we are just going to integrate it. I'll take the mu naught upon 4 pi outside and we'll integrate this thing. And in the denominator we have r cube. Tell me, is the r distance constant or it is also changing? It is definitely changing. So I need to take this r cube also inside, and it will be sine of 90 minus theta will be cos theta, and this is r square. Now I just need a little more of trigonometry to get the final result. We'll just pull it upwards. Okay, so let's say कि this distance I'll take as some d distance, the perpendicular distance of point P from the wire. So any r vector, if I look at this triangle, let's erase the extra terms from this triangle, and you just see what's important. This is your r vector of the element, this is the d distance, and this was some angle theta. So this was 90 minus theta, and if you see the relation that d is equals to r cos theta, or I can write d by cos theta is equals to r. Correct or not? Alright. Also, what about this dl? Because I need to write this dl also in terms of the angle theta. So you just see that dl is actually this length. If I say ki this height of the right angle triangle here is some y, then dl is nothing but dy only. The little extension in this side is dl. Okay. Now how do I write y? So y is written as r sine theta. Great. Or since I don't know r2, I can write in terms of tan theta also. So y will be equals to d tan theta. And now if I differentiate this y, so I'll get dy is equals to d differentiation of tan theta is secant square theta and d theta. Simply that. If I use both of them, and we are just about to prove this very interesting result. So I'll put the dl and dy here in the formula, mu naught I upon 4 pi, and cos theta remains as it is. Here I can write dy or dl as distance d times secant square theta d theta, while this d and r is d by cos theta, so d sec theta, so r square becomes d square secant square theta. That's it. I hope you guys got the point ki what's going to get cancelled. So sec square theta gets cancelled. One, this d distance gets cancelled. And inside the integration, I only have cos theta d theta, where this angle theta will go from minus beta to alpha. And I get my formula. Your magnetic field is mu naught I by 4 pi d. Integration of cos theta d theta is sine theta, and the sine theta ranges from minus beta to alpha. This is how. These 2 points were quite crucial in deriving this formula, and just by putting this, I'll get the final formula. We'll write it on the next page. It's a very important formula. Now you know the proof of it. So this is your current carrying wire. This was the d distance. This is point P. The top part was making angle alpha. Bottom part was making angle beta. Carries the current I. So magnetic field I got as mu naught I by 4 pi d distance sine of alpha, if I put alpha, and minus of sine of minus beta, which will get me the plus sign. So plus sine beta. And this is the net magnetic field. So you got the formula. Now you understood the finite wire formula for the magnetic field using Biot-Savart law, and it's much sufficient for all of your exams to understand how did we get this formula. Now if you understood this formula, and we are going to use it for much more better scenarios, like for infinitely large current carrying wire. For this, we are just going to put alpha angle as 90 degrees and beta angle also as 90 degrees. Because if I look at this diagram, it becomes infinitely large, so this line joining the point is going to become vertical, just parallel to the wire, so this angle becomes 90, and same thing happens with the downward angle as well. So just put the values, and what you will get: magnetic field due to infinitely large current carrying wire, mu naught I 4 pi d, sin 90 is 1, sin 90 is 1. So you got the formula, mu naught I by 2 pi d. Great. And this formula you have been using many times. Now you can apply the same concept for any type of wire and any type of angle. Let's take an example here. Suppose there was a wire and it carries current. Understood that length of the wire is nowhere to come in this formula, because it is adjusted by the distance and the angles, so it is already taken care of, so we need not worry. Okay, information is, there is a current carrying wire. The point is at a distance d from the wire. The topmost point makes angle 53 degrees, bottommost point makes angle 37 degrees. I need to get the magnetic field. Just use the formula, mu naught I by 4 pi d sin 53 plus sin 37. Okay. Everyone knows sin 53 is 4 over 5 and sin 37 is 3 over 5. So 7 by, and we can just multiply this 4, so 20 pi d mu naught into I. And remember that this magnetic field, if the current is going upwards and the point is on the right side, so I'll find out the direction just by this cross product of I and this distance r. So I is in this direction, put your fingers along this, and r is in this direction, do the cross product. The direction of thumb is the magnetic field, which is into the plane, and the sign of minus k cap can be written as this circle and a cross, and sign of plus k cap is this circle and a dot. No, it's in the minus k cap direction. We got the answer. Same result we can apply for any sort of wire. Another important point is a semi-infinite wire. Semi-infinite wire means कि I know its starting point but ending point is at infinity, so I don't know technically where is it. ठीक, starts from here. And it goes until infinity. Okay. Now look at the trick. They can modify the situation. They can tell you carries current I. My point is not here. Okay? If my point was here, I can easily find the magnetic field. It will be mu naught I by 4 pi d. So I'll put 2 points here. Point A directly aligned with the end point, and point B which is little bit below. ठीक है. The line joining the endpoint and the B makes angle 30 degrees with the horizontal and like this. To find the magnetic field at A, it is quite very easy. It will be mu naught I by 4 pi d, because one of the angles, okay, because one of the angles is 90 and the other angle is just 0. Look at here. The end point, the line joining end point makes 0 degrees with the horizontal, while the other end it makes 90 degrees. Okay. While the magnetic field at point B is quite crucial, let's see. One of the angles will be definitely 90, because the alpha angle is when the line joining these endpoints and the B is parallel to the current carrying wire, so one is definitely 90 degrees. What about the other one? Is it 30 or should I keep it as minus 30? Remember that in this formula, when I was taking the angles also here, one of the angles alpha was in the clockwise and the other angle beta was in the anti-clockwise. That's why I had put the minus beta here in the limits. Minus beta means we are going in the opposite direction. So I got plus in the final result of the integration. While as in this example, I see that the line joining endpoint and B is going in the clockwise, and the line joining the upper endpoint and B is also going in the clockwise. So I must put minus 30 here. That only will give me the correct answer. Okay, just remember this point, ki how we are taking the angle. Both are going in the clockwise sense. So I should keep a minus sign in one. Answer will be mu naught I by 4 pi d. Sin 90 is 1, sin 30 is 1 by 2. So I get magnetic field at point B mu naught I by 8 pi d. This is how you are going to use this formula. Now let's take the other formats for the Biot-Savart law. An arc. Okay. So magnetic field due to an arc. Let's say we have an arc here, okay, and at the center of the arc I need to get the magnetic field. You would remember similar kind of concept in electrostats also, correct? It's carrying the current in this direction. Look at the direction of current. If it's a curved wire, draw a tangent and it should go in the direction of current. So this is the tangent going like this. Look at the fingers, okay? The point P is below. So if I take an R vector, curling fingers should be like this, clockwise sense. So again the thumb is pointing inwards. That means magnetic field due to this at point P will be inwards. This is the current, this is R, so it is going inwards. Okay. Now for this again, I need to apply that Biot-Savart law. Good thing is now the distance of any element from this point is quite very easy. Okay. The angle between DL and R is also 90 because tangent is always perpendicular to the radius. So if I write this thing, little magnetic field mu naught upon 4 pi I dl cross R. Now R is nothing but perpendicular, so I need not write R at all, and in the denominator it will be just R square. Get it? Because R cap and dl are already perpendicular, so it will be sin 90 here. That's it. And I need to integrate it. Okay? R distance is same for all, so it comes out of the integration. Current is definitely the same. Now integration of dl. dl is what? Little length of this arc. So what's the total length of the arc? I know length of the arc formula is r into angle theta. Put it here. So mu naught I by 4 pi r square, and dl is r into theta. Just cancel one of the r and you get the formula mu naught I by 4 pi r into angle theta. That's it. Theta has to be in radians. If it is coming out like this, has to be in radians, like this. So tell me, if we are finding the magnetic field at the center of a complete ring, so what will be the angle theta? At the center of a complete ring, angle theta will be 2 pi. So our answer should come out to be, due to the ring at the center, correct, mu naught I theta by 4 pi r. So I is this only and theta becomes 2 pi mu naught I by 2r. I guess you guys would remember this formula. Now you can get the answer for any kind of r. And the question which most of the competitive exams want to ask is, suppose I have this infinitely large wire, okay, semi-infinitely large wire, and at the end I have connected an arc, and at the end of the quarter circular arc I have connected another semi-infinitely large wire. Let's say like this. Same current is going like this, okay, same current is going. They're asking key at the center of this arc, r distance. I hope you know that quarter circle, this angle is 90 degrees, pi by 2. So I can get the magnetic field due to this semi-infinite wire, due to this semi-infinite wire, and due to this arc. Tell me, is the direction of magnetic field due to all the three components same? Definitely yes. This is current carrying wire, so IDL cross R into the plane, correct. This is current carrying wire, so again IDL cross R into the plane, and for this also, this is the direction of DL and this is your R. So IDL cross R again into the plane. So all the three magnetic fields are going to get added and they are all into the plane. Due to this wire, semi-infinite wire, answer is mu naught I by 4 pi R, correct. Due to this, it is again mu naught I by 4 pi R. And due to this curve, the curve arc, it will be mu naught I, angle theta is pi by 2, and 4 pi R, the radius is R itself. Okay? So either you cancel the pi in this or you take the 4 pi R common, whichever you like, it's your choice. Let's just cancel it. So here I'll get mu naught I by 2 pi R, and here I'll get mu naught I by 8R. I'll keep the answer like this. This will be your final answer. The combination of different current carrying wires. Okay. Fine. Let's move on. Let's take one more example of magnetic field. Then we are going to move on to the other parts of this chapter. The force on a charged wire, the force on a current carrying wire, and the magnetic moment. These 4-5 things are very important. Okay. Magnetic field at a point on the axis of a current carrying coil, circular current carrying coil. Okay. This is a coil and we are looking it from sideways. Okay, this is perpendicular to the plane of the board. This is the point. Current is like this. Okay. Now the issue is that the current carrying wire is like this and it is out of the plane, and R vector is like this. If I do ideal cross R, the magnetic field will be not just into the plane, rather at an angle. Correct or not? If I look at the topmost point, the current is going inwards and the R vector will be like this. So if I do ideal cross R, the magnetic field will be like this. And if I look at this portion, which is just inside the plane, then R is like this, and the current carrying wire, I have to curl my hand like this, and it will be like this. So the magnetic field is going to make this kind of direction, okay. And here if I see that due to this current carrying coil, the magnetic field direction will be along the axis, because all of these components are going to result only on this component. Okay. So I know that this distance is going to be same for all, not an issue, not a very big deal. This distance will be same. I'll say this angle is some theta angle. This is r radius and this is x distance. All the magnetic fields, whichever direction we are getting, I need to just take the component of that magnetic field, and then I'll decide what to do. Take. The thing is if I write this r, it will be under root of r square plus x square. So the issue is if you take an element and you do the integration, just need to take care of this r distance and that component of magnetic field. So for this we are not going to do the derivation, we don't have that much time, so I'll just write the formula. So mu naught I r square under root of r square plus x square cube. Get it? Always remember, if you forget whether it is r square in the numerator or is it cube or not, just remember the dimensions. The dimensions of magnetic field should be mu naught I by 2 pi r or 2 pi d or just 2r, anything like this. Okay. So mu naught I is fine. In the denominator I get a dimension of r. So if you see, this is under root of r square, that means it will just give me r, and then it is cube, and then it is r square. So r square and cube cancels and only one r remains. So this is how you should remember or quickly justify the formula which you remember. Okay. Alright, fine. Now see, I found this magnetic field at the point P along the axis. And now I want to verify at the center of the ring, which we just found, is it coming out to be correct or not, by just putting x as 0. So at the center, x is equals to 0. Put it here, I'll get the magnetic field as mu naught I r square and 2 pi, sorry, there is no pi here, it is just 2 only. And under root of r square plus x is again 0, so 0 square 3 by 2. Okay, we have already put the under root, so no need to put 1 by 2. So it is mu naught I by r square and 2, and this becomes r to the power 3. R square and this cube cancels, and I got the formula of mu naught I by 2r, magnetic field at the center. Okay. Alright, let's move on. Next is magnetic field due to a solenoid. Due to a large solenoid. Okay. So let's suppose we have a quite large solenoid, and I want to find the magnetic field inside the solenoid at some point. It's carrying some current I. The total number of turns would be some capital N, but we write small n. The number of turns per unit length. Number of turns per unit length. Magnetic field inside the solenoid is mu naught Ni. Tell me how the dimension of the magnetic field is correct, because this N already has L in the denominator. So mu naught, total number of turns I upon the length. So I got the dimension correctly. If I want to find the magnetic field at the end point, near the end point but inside, then it comes out to be mu naught Ni by 2. The two formulas you should remember. Okay, so this is about the solenoid. Now to talk about the magnetic field lines of the solenoid, so you should remember that for a finite solenoid the magnetic field lines are just like a bar magnet as it is. That's it. Okay. Now we wrote the magnetic field. I'll just quickly summarize all of this. So due to infinitely large wire, it was mu naught I by 2 pi d. The important formulas only we'll write. Due to a coil at its center, it is, now if a coil has n number of turns, then it will be mu naught number of turns into I upon 2r. Due to a solenoid, inside the solenoid, it is mu naught small n into I. Just remember, number of turns and small I are two different quantities. Okay. Now you would have heard about the Ampere's circuital law. This thing we used to find the magnetic field due to this current carrying wire itself. The Ampere's circuital law, the statement is important. It says that the line integral of B dot dl around a closed loop, we can say a closed path, is directly proportional to the current enclosed or the current passing through the plane of the loop. Okay? This thing. Enclosed in the loop means current passing through that closed loop. So that's your Ampere's circuital law. This is the magnetic field, B vector. dl is the length of little arc, or let's say element on the loop, little portion of the loop. I is the current enclosed means passing through the plane of the loop. Ampere's circuital law. Okay. Now, if I want to get a charged particle in the magnetic field, now if a charged particle is moving, then it's going to produce magnetic effects. Also we know that in the electromagnetic induction, if the magnetic field is changing, it's going to produce electrical effects, the electric field, induced electric field. So the formula of the net force on the charged particle, including the electrostatic force, the net Lorentz force, if I say charge is q, it's moving with velocity v, then the Lorentz force is q v cross b in the absence of external electric field, and in the presence of external electric field, it is q e electrostatic force and q v b the magnetic force. Electric force, the magnetic force. Okay. Now see, depending upon the direction of velocity and the direction of magnetic field, will get different formulas or different scenarios where the charged particle is moving. Firstly, you need to understand that the magnetic force is always perpendicular to the velocity of the charged particle and also the magnetic field. one of the very important points. Also to the magnetic field. So how does the motion look like? We'll take a very straightforward scenario. There is a region of perpendicular magnetic field. Cross means it is going into the plane. It's uniform. The magnitude is same everywhere. Okay. If I say the value of magnetic field is B and it is going into the plane, a charged particle enters this field with a velocity V. Its charge is Q and it has mass M. Q by M ratio is given. Let's say the force on it will get it through this formula V cross B, cross product. Now again cross product, right hand rule. V is in this direction, B is into the plane. So you need to be carefully maneuvering your hand so as to get the cross product. So firstly, I'll put the fingers along V, can be like this, can be like this. I need to curl in the direction of B. B is going into the plane, so the curling will be like this. Now just notice the direction of thumb. V cross B, curling into the plane. So V cross B, the direction is upwards. That means the electrostatic force comes vertically upwards. Remember that the force is always perpendicular to the velocity. Tell me what kind of motion I know in which the force is perpendicular to the velocity. It's the circular motion. So this charged particle is going to perform circular motion, but only till it is inside the magnetic field. Okay. Alright, fine. So they ask, is it a circular motion? Yes, it is a circular path inside the magnetic field. Okay, it's a circular path. How do we get the radius of the circle? The radius of circle will easily get using the centripetal formula. Centripetal force, I'll just write the centripetal force is mv square by r. The magnetic force is Q VB, and here I can see V and B both are perpendicular, so I can easily remove the cross product in the sine theta. So R comes out to be mv upon QB, standard formula. Must remember the radius of the curvature of the circular path. Very straightforward. Next is, if it is going to move in the circle and suppose it's in the very vast magnetic field, okay? If it moves in the magnetic field and completes the circle, please remember it should complete the circle, then only, and completes the circle. If it is allowed to complete, if the magnetic field is everywhere present, then only, then the time taken will come out to be, you can easily write, you have the speed, you got the radius, you can get the circumference 2 pi r, and speed, your r is mv, so we'll get 2 pi m, vv gets cancelled, so qb. Another great formula, time period for the circular path. Okay. So you should remember that while discussing the magnetic force, we should always remember the basics, the cross product, like this. Okay. Next is, if we are moving a charge, it experiences force. Then if we are moving a current carrying wire, it should also experience a force, correct? Because current carrying wire has charge already present in it, definitely. Force on a current carrying wire. Okay. Suppose I have any random wire. Okay, we'll start with the most easiest one, a straight current carrying wire. It carries I current. It's moving like this with the speed V, and into perpendicular magnetic field. ठीक है? Okay. Now, all right, wait. The length of the wire considered here is L. Okay. This current carrying wire is going to experience a magnetic force. It is not moving. It's not moving in this scenario. If it were moving, then EMF will be induced. We are not talking about that. That's the next chapter. We are just finding the force. So for the force, the wire is not moving. Only the charge is moving along the wire. Tell me, is the charge moving? If I consider the current as a positive charge, is it moving upwards? Yes, it's moving upwards. Magnetic field is into the plane, so what will be the direction of force? Leftwards. The direction of the force will be given by the direction of current and the magnetic field. That means I is a scalar quantity, so I need the vector L in direction of I. Just remember, L is in the direction of I. And do the cross product. This gives the direction of force. The direction of force. Check. The formula comes out to be ILB, or you can say BIL. But I know that this is a vector quantity. So how do I write it in terms of vectors? Just like Biot-Savart law, we have the formula. It is I dl vector cross B. Now you know why did I write this thing as L cross B? For this uniform wire, now the dl is straightforward, so I need not worry. And suppose ki the wire is of some very different shape, maybe like this, and the current is flowing in it. Magnetic field is everywhere. If the wire is in a plane perpendicular, then the length you have to take for this integration will be L effective length. This L effective is just the displacement from starting to the end point of the wire AB. So the formula of the force becomes I L effective into B, like this. For example, I have a semi-circular wire. The current is flowing in it. Get it? It's placed in the external magnetic field. B is the magnetic field. The force will be, tell me, I L effective B. The radius of the wire you have been given is R here. So should I write the L effective as pi r, the circumference of this wire, or just the shortest distance displacement, which is 2r? Tell me. I said kids, the shortest distance doesn't matter what's the shape of the wire, so it is 2r. 2r into B. And this will be the magnitude of the force. The direction you can again easily get. I is in this direction, or L effective is in this direction, so L cross B, that means towards the left. That's the direction of your magnetic force. Alright. So these were some of the very, very important concepts of this chapter. The magnetic field to a straight current carrying wire, coil or a loop, arc, solenoid, and the magnetic force on a charged particle and a current carrying wire. Last part of this I want to discuss is the magnetic moment of a current carrying wire and a charge moving in circular motion, okay, periodic motion. Magnetic moment. It's just like the dipole moment for electric dipole. Here the magnetic moment for magnetic dipole or a current carrying wire. Firstly, it's for the coil. If I have a current carrying coil like this, it's carrying current in this direction. Now tell me what's the direction of magnetic field. You can easily get it from the right hand rule. So what you do? You curl the finger along this curved current carrying wire. The direction of thumb gives the magnetic field, and the same is the direction of your magnetic moment. Take it. So using the right hand rule, you will get the direction of magnetic moment. Magnetic moment, and it's a vector quantity using right hand thumb rule. Just like magnetic field. Okay. If this wire has n number of turns, then the magnetic moment is simply NIA. And here the direction is normal to this plane, that means in the direction of its magnetic field. So I have put n cap. I'll write it. What is n cap? In the direction of magnetic field. Due to this current carrying coil. ठीक है, NIA, very standard formula. N is the total number of turns, I is the current. And area is the area of this circular loop. Get it? Same formula you have to use for a charged particle in a circular path. A charge revolving in a circular path. Okay. If a charge is continuously moving in a circular path with angular frequency omega, the radius b r, then you need to simply write the frequency, which is omega upon 2 pi, standard format. Omega is angular velocity. Magnetic moment will come out to be, the Ni part will be simply written as Q into the frequency, and the area will be area only. It will be upon 2 pi, and the area of the loop will be pi r square. Pi gets cancelled, so it is Q omega r square by 2, magnetic moment. Same formula we can use for extended charge configurations like a rod. If a rod is rotating, in external magnetic field, a charged rod is rotating, a charged rod is rotating, so the associated magnetic moment can be simply written as charge of it, the charged rod, upon 2m into its angular momentum. Okay, you get the magnetic moment. Assume that the total mass of the rod is m. Whatever is the length of the rod, you write the moment of inertia. So angular momentum will be written as I into omega, and thus you will get the similar kind of formula for this also. And that's how we solve the concept of magnetic moment. Okay, alright, fine. One more thing, there is bar magnet, and magnetic moment plus the concept of bar magnet is just analogous to an electric dipole. Electric dipole. Bar magnet has north and south poles, let's suppose like this. So we'll write a quantity which is called pole strength. Small m is the magnetic pole strength, minus m for south and plus m for north. Its distance is d. Just like a dipole, plus and minus. So instead of pole strength, here we write the charge. So plus q and minus q. The distance is d. What is the dipole moment here? It is q into d. The direction of d will be from negative to positive. Same thing here also. The direction of m the magnetic moment will be small m into d, and it is in the direction of south to north. Dipole experiences the torque, correct. So the torque is written as P cross the external field, and here also magnetic dipole or a bar magnet experiences torque in the external field, it will be M cross B. Remember that this is capital M, magnetic moment. A dipole placed in external field possesses some potential energy. Its electric energy, electric potential, which is minus P dot E. Now the bar magnet also possesses some energy, and it will be minus M dot B. So these are your important concepts of magnetism, magnetic effects. I hope this clarified little bit of your doubts, and just use on these formulas, practice on more problems, and stay tuned for more topics. Thank you.